Hi, today we are going to learn the hybridization. In this topic, we will describe the hybridization process of atomic orbital of atoms. At the end of this lesson, students should be able to describe the formation of hybrid orbitals of a central atom for sp³d and sp³d² using appropriate examples. Student also needs to illustrate the hybridization of the central atom and the overlapping of orbitals in the molecules. For hybridization of sp³d and sp³d², the elements in the third period and beyond, molecular geometry cannot always be accounted by assuming only s and p orbitals hybridize because of the existence of the empty d orbital, which is produce an expanded octet. The formation of the molecules with trigonal bipyramidal and octahedral geometries must include the d orbitals in the hybridization concepts. Now, let's discuss the sp³d hybridization. sp³d hybridization is a mixing of one s orbital, 3 p orbitals, and 1 d orbital to produce 5 sp³d hybrid orbitals. The sp³d hybrid orbitals adopt a trigonal bipyramidal geometry. The bond angle between the bonds are 90 degree and 120 degree. This diagram shows the orbitals involved in hybridization to form sp³d hybrid orbitals. Now, let's discuss the hybridization of phosphorus atom in phosphorus pentachloride molecule. To determine the hybridization of the phosphorus atom in a molecule, first we need to draw the Lewis structure of a molecule. From the Lewis structure, we can see that the phosphorus atom contains 5 sigma bonds. The phosphorus atom must have 5 unpaired electrons in the valence atomic orbitals. The 5 orbitals hybridize and allowing the molecule to form 5 sigma bonds. At ground state, phosphorus atom has 5 valence electrons, while the chlorine with 7 valence electrons. According to the valence bond theory, it is impossible for a phosphorus atom to form 5 covalent bonds with 5 chlorine atoms because at ground state, phosphorus atom has 3 unpaired electrons and can form only 3 bonds with the other atoms. Thus, phosphorus atom undergo hybridization. The hybridization process are as follows. At ground state, the phosphorus atom has 5 valence electrons. In order to produce 5 unpaired electrons, 1 electron is excited from 3s to 3d empty orbital. Mixing 1s orbital, 3p orbitals, and 1d orbital will generate 5 sp³d hybrid orbital. Therefore, the hybridization of phosphorus in the PCl5 molecule is sp³d hybridization. To determine the molecular geometry of a molecule, we can consider the repulsion of 5 sp3 hybrid orbitals. They are arranged in trigonal bipyramidal. Since in each of the orbital consisting of bonding pairs, the molecular geometry obtained a trigonal bipyramidal. Overlapping of each sp3 hybrid orbitals of phosphorus atom with 5 p orbitals of chlorine atoms forming 5 sigma bonds. The molecular geometry obtained trigonal bipyramidal with bond angle 90 degree and 120 degree. Now, let's consider the hybridization of the selenium atom in selenium tetrafluoride. First, we need to draw the Lewis structure of a molecule. From the Lewis structure, we can see that the selenium atom contains 4 sigma bonds and 1 lone pair. The selenium atom must have 4 unpaired electrons and 1 lone pair in the valence atomic orbitals. The 5 orbitals hybridize and allowing the molecule to form 4 sigma bonds and a lone pair. At ground state, selenium atom has 6 valence electrons, while the fluorine with 7 valence electrons. According to the valence bond theory, it is impossible for a selenium atom to form 4 covalent bonds with 4 fluorine atoms because at ground state, selenium atom has 2 unpaired electrons and can form only 2 bonds with other atoms. Thus, the selenium atom will undergo hybridization. The hybridization process are as follows. At ground state, selenium with 6 valence electrons. In order to produce 4 unpaired electrons, 1 electron is excited from 4p to 4d empty orbital. Mixing 1s orbital, 3p orbitals, and 1d orbital will generate 5 sp³d hybrid orbitals. Therefore, the hybridization of the selenium atom in the selenium tetrafluoride molecule is sp³d hybridization. To determine the molecular geometry of a molecule, we can consider the repulsion of 5 sp³d hybrid orbitals. All the orbitals are arranged in trigonal bipyramidal. Since we have one lone pair in the orbital, thus the molecular geometry obtains a seesaw or the distorted tetrahedron. Overlapping of each sp³d hybrid orbitals of the selenium atom with 4 p orbitals of fluorine atoms, forming 4 sigma bonds. The 5th sp³d hybrid orbitals accommodate a lone pair electrons. The molecular geometry will obtain seesaw or the distorted tetrahedron, with bond angles must be less than 90 degree and less than 120 degree. Now, let's discuss sp³d² hybridization. sp³d² hybridization is a mixing of 1s orbital, 3p orbitals, and 2d orbitals to produce 6 sp³d² hybrid orbitals. The sp³d² hybrid orbitals adopt an octahedral geometry. The bond angles between the bonds are 90 degree. This diagram shows the mixing of orbitals to produce sp³d² hybrid orbitals. Now, let's discuss the hybridization of the sulfur atom in sulfur hexafluoride molecule. To determine the hybridization of the sulfur atom in a molecule, first we need to draw the Lewis structure of a molecule. From the Lewis structure, we can see the sulfur atom contains 6 sigma bonds. The sulfur atom must have 6 unpaired electrons in the valence atomic orbitals. The 6th orbital hybridize and allowing the molecule to form 6 sigma bond. At ground state, sulfur atom has 6 valence electrons, while the fluorine with 7 valence electrons. According to the valence bond theory, it is impossible for a sulfur atom to form 6 covalent bonds with 6 fluorine atoms because at ground state, sulfur atom has 2 unpaired electrons and can form only 2 bonds with other atoms. Thus, the sulfur atom will undergo hybridization. The hybridization process are as follows. At ground state, sulfur atom with 6 valence electrons. In order to produce 6 unpaired electrons, 2 electrons are excited from 3s and 3p orbital to fill the empty 3d orbitals. Mixing 1s orbital, 3p orbitals, and 2d orbitals will generate 6 sp³d² hybrid orbitals. Therefore, the type of hybridization of a sulfur in a molecule is sp³d² hybridization. To determine the molecular geometry of a molecule, we can consider the repulsion of 6 sp³d² hybrid orbitals. All the orbitals are arranged in octahedral. Since all the orbitals was filled with bonding pairs, therefore the molecular geometry obtained octahedral. Overlapping of each sp³d² hybrid orbitals of sulfur atom with 6 p orbitals of fluorine atoms forming 6 sigma bonds. The molecular geometry obtained an octahedral with bond angles 90 degree. Now, let's discuss the hybridization of xenon atom in xenon tetrafluoride molecule. First, we need to draw the Lewis structure of a molecule. From the Lewis structure, we can see the xenon atom contains 4 sigma bonds and 2 lone pairs. The xenon atom must have 4 unpaired electrons and 2 lone pairs in the valence atomic orbitals. The 6 orbital hybridize and allowing the molecule to form 4 sigma bond and 2 lone pairs. At ground state, xenon with 8 valence electrons, while the fluorine with 7 valence electrons. According to the valence bond theory, it is impossible for a xenon atom to form 4 covalent bonds with 4 fluorine atoms because at ground state, xenon atom has no unpaired electrons and cannot form any bonds with other atoms. Thus, xenon atom will undergo hybridization. The hybridization process are as follows. At ground state, xenon with 8 valence electrons. In order to produce 4 unpaired electrons, 2 electrons are excited from 5p orbitals to fill the empty 5d orbitals. Mixing 1 s orbital, 3 p orbitals, and 2d orbitals will generate 6 sp³d² hybrid orbital. Thus, the hybridization of the xenon atom is sp³d² hybridization. To determine the molecular geometry of a molecule, we can consider the repulsion of 6 sp³d² hybrid orbitals. All the orbitals are arranged in octahedral. Since 2 of the orbitals was accommodated by 2 lone pairs, therefore the molecular geometry obtained square planar. Overlapping of each sp³d² hybrid orbitals of xenon atom with 4 p orbitals of fluorine atoms forming 4 sigma bonds. The 5th and the 6th sp³d² hybrid orbitals accommodate lone pairs electrons. The molecular geometry obtained a square planar with bond angle 90 degrees. How can we predict the hybridization of a central atom? Here are some tips. Count the total number of electron pairs, includes the lone pairs and the sigma bonds that bonded to the central atoms. For example, the xenon atom in xenon tetrafluoride molecule. In this molecule, the xenon atom contains 4 sigma bonds and 2 lone pairs. That gives 6 electron pairs. All the electron pairs are arranged in 6 orbitals of octahedral. Thus, the type of hybridization of this atom is sp³d² hybrid orbital. From this lesson, we can summarize that by mixing 1s orbital, 3p orbitals, and 1d orbital, we produce 5 sp³d hybrid orbitals. These orbitals are arranged in trigonal bipyramidal. Mixing 1s orbital, 3p orbitals, and 2d orbitals, we produce 6 sp³d² hybrid orbitals, and they are arranged in octahedrals. You also can refer to this table to summarize all types of hybridization that we have learned in this topic. Now, let's try these questions. You can check your answer in tutorial video. This is an assignment for you to complete. You can watch this video again if necessary as a guide for you to solve these questions. So, that's the end of our lessons today. We'll see you next time. Bye!